Thanks. So yeah, I'm Adam Bouland. I'm an assistant professor here at Stanford. I'm going to tell you about the state of quantum computing and what it means for the future of the blockchain. So it seems like every day you open up the news, you see another article about a new breakthrough that's happening in quantum computing. Like ever since this experiment that occurred in 2019 that made the New York Times, and there's another experiment last December, another one just a few weeks ago by Microsoft. What's going on here? Well, what's happening is that there's major progress towards building a quantum computer. We're now doing the first quantum computations which are beyond classical computers. There are some computations we can do with these quantum chips that take on the order of minutes that would take thousands of years to simulate with a classical computer. And we're also seeing the first quantum devices that are performing something called quantum error correction that I'll explain a little more in this talk. So the TLDR is kind of what's happening is quantum computers are getting better. They're still very far from breaking today's crypto, but they actually do pose a future threat to blockchain and other technologies because they break a number of public key crypto systems which underlie these, particularly some of the digital signatures used in Bitcoin and other protocols. So in today's talk, I'm going to tell you about a little bit about this threat to the blockchain. Like, what is a quantum computer? Where are we in the long journey towards building one? What did these articles that are in the New York Times achieve? And what's kind of left to do? Okay, so the starting point of quantum computing is that the quantum mechanics has a really strange property. If you have a system of quantum mechanical particles, every time you add a particle to the system, the number of parameters that you need to describe the system doubles, as it grows exponentially in the number of particles. So put this together, you have like 300 quantum particles. That means there's, the number of bits or something you need to describe the system is more than the number of atoms in the universe, right? This is insane. And this is actually one of the reasons that quantum mechanical systems are extremely difficult to simulate with today's computers. Actually, a lot of our CPU cycles at major DOE, National Lab Quantum Computing Centers is spent simulating quantum systems. Now in the 1980s, Richard Feynman asked if we could take this difficulty and turn it on its head. So rather than viewing this as an obstruction to simulating quantum systems, could we instead use quantum mechanics to perform some computations that are more powerful than we could classically? That's like, could we use this in a positive setting to build a more powerful computer? And the answer to Feynman questions is really far from obvious. The main issue is that quantum mechanical systems are not only are they exponentially powerful, but they're also in some sense exponentially secretive. Even though they have these 2 to the n parameters that describe them, like this huge exponential number of parameters to describe the state of a quantum system, you can only manipulate those parameters in certain ways. You can only learn very coarse-grained information about the parameters. So kind of like you have like a limited I/O model with this kind of very powerful sort of underlying physical theory. So the central question of quantum computing is, can you use this kind of hidden exponential parameter space in order to accelerate any sort of useful computations? Now, the first answer to this from the theory side came in 1993 when Bernstein and Vazirani and then Dan Simon gave the first evidence that quantum computers can actually solve a problem exponentially faster than classical computers. This was, however, for a really toy problem that was very interesting from a mathematical standpoint, but wasn't useful for anything. It was really kind of just designed to showcase the power of the quantum device. But this was followed very shortly by Peter Shor's result in 1994 that a large-scale quantum computer would be able to efficiently factor numbers. That is to say, given an integer n, which is a product, say, of 2 primes p and q, tell me what primes p and q I need to multiply to get back the number n. So this is a problem where the answer is very easy to check, but it's very actually hard to find p and q given the integer n. And this problem is believed to be exponentially difficult for classical computers as a function of the number of bits needed to represent the number. And this is the basis of today's RSA crypto system that, powers today's HTTPS protocols. It turns out that Shor's algorithm easily extends to a related problem called the discrete log problem. And this breaks a huge number of public key crypto systems like Diffie-Hellman, elliptic curve crypto. This is what breaks the digital signatures that are used in blockchain protocols. So these theoretical results in the 90s launched the quest to build a large-scale quantum computer and to try to better understand potential applications of these. Like, what if we built a large-scale quantum computer, other than factoring numbers and reading everyone's email, what would be the long-term applications of these devices? And what we've learned over the last 30 years of quantum computing theory is that large-scale quantum computers will only be better than classical computers at very specific computational tasks. They are not like building a faster GPU or building a faster CPU or something like that. There's some computational tasks they're a lot better at than normal computers. There are other tasks they're actually worse at, or at least there's no advantage for them at. So what are these problems that quantum computers will be good for? Well, some examples are breaking public key crypto, like Bitcoin digital signatures. This is something we can do with a large-scale quantum computer. We don't know how to do classically. That's kind of only breaking things. We can also build things. So another major application of quantum computers would be problems in quantum chemistry and materials. So you can use a quantum computer to very efficiently simulate quantum mechanical systems. And we believe that both of these applications of quantum computers are something called strong exponential speedups. That is to say, the quantum algorithm is actually exponentially faster than the classical algorithm at solving the initial task. On the other hand, there are other potential applications of quantum computers in tasks like machine learning and optimization. However, the degree of quantum speedup for these tasks is much less. They're sometimes called a weak or a polynomial speedup. And it's not entirely clear if these will be useful in the long-term future. This is mostly because quantum computers have slower clock speeds than like your CPU or GPU. So there's an initial slowdown they have to overcome in order to become practically relevant. If you have exponential improvement in scaling, you overcome that initial setback very quickly. But if you have a more modest improvement, whether or not these are useful depend on on the parameters of future quantum computing hardware. Okay. And this really has the potential to change the world. So, breaking public key crypto would be a big deal. Even if we're very far away from building a quantum computer, even if we're decades away from it, the threat that one might exist in the future is enough to force changes to our crypto systems today. Because, like many crypto applications, you want forward secrecy, like you want the message you're sending now to still be secret 10 or 20 years from now. And so as a result, the NIST is currently building a post-quantum cryptographic standard and trying to standardize a post-quantum crypto scheme that we can all use in the future that will be resistant to quantum attack. Second, I think this quantum chemistry application has world-changing potential too. If you can simulate quantum systems on a quantum computer very quickly, maybe we'll be able to design drugs or materials, on a quantum computer by simulation, the same way that we design, bridges or airplanes by simulation on a classical computer today, right? Now, beware of hype in this space. There's a huge amount of hype in the quantum computing space right now. But I just want to say that underlying it, there is some real potential. I think one of my favorite quotes is quantum computing is both overhyped and undersold. Oftentimes the specific applications of quantum computers are being very overhyped in the media, but undersold in the sense that it is actually a fundamentally new type of computer that will enable us to solve some problems we could have never solved possibly before. So that's a major advancement. Okay. So I hope I convinced you quantum computers are cool. I hope you're all like, yeah, great. Let's build a quantum computer. Okay. What's the difficulty? It turns out it's extremely difficult to build a large-scale quantum computer. It's more like putting a human on the moon and less like building an app in a year or something like this. And the central issue with building large-scale quantum computers is noise. Okay, so what do I mean by noise? So what happens if you have a Python program and you hit enter to execute the program? Well, it runs through some interpreter or, depending on your language, some compiler. And your computer compiles it down in some very low-level language like assembly. And that contains very low-level instructions as to what manipulations of bits your classical computer should do. Like if bit 17 is 0, flip bit 18. And that ends up going into some transistors in your CPU, which then execute that exact instruction. So noise is what happens when that operation that you wanted to occur, that low-level bit operation, was performed incorrectly. And when people started building classical computers in the 1940s, like from vacuum tubes, actually computers had a very large error rate and were very faulty. So there's a famous story of the first bug, Grace Hopper's first bug being an actual moth that was lodged in the vacuum tube that caused it to fail. They were not today's CPUs. So, and people in the 1950s, for example, worried a lot about error rates in classical computers. Like von Neumann actually wrote some central work trying to prove that you could error correct faults that occur in the process of classical computing. What happened in the last 50 years is we just totally engineered this problem away. Like the modern error rate on a modern CPU per bit operation is in the ballpark of 10 to the minus 15. Your CPU is basically perfect. Unless you're doing extremely large-scale scientific computation, the errors that occur in your laptop are basically irrelevant. Okay. So what happens when we try to build a quantum computer? Well, you can define kind of a generalization of a classical program to a quantum program. And it compiles down to some low-level operations that are called gates that act on individual quantum bits or qubits. Okay? And the issue is that we can build quantum computers that execute this chain, but the error rate of these quantum computers is really high. The error rate per individual operation that acts on, say, 2 quantum bits, like the analog of if bit 17 is 1, flip bit 18, the error rate of that is something like 1% to 0.1%. That's really high, and that limits how big of a quantum computation you can perform before your system kind of devolves into errors and noise. That's the central limiting factor with quantum computers. Okay. So now, at the same time that people came up with the quantum computers as a theoretical model in the 90s, they realized that noise might be a problem, and they came up with a theoretical solution to this problem as well. The theoretical solution is called quantum error correction. So the basic idea is you can take a quantum computation you want to perform and redundantly encode your quantum information in a much larger number of qubits, kind of analogous to how if you have a classical computation you want to perform or classical data you want to perform, you might store it in a redundant manner, like for some RAID setup or something like this, right, in order to preserve it in case of faults, right? And in particular, they proved a really key result in quantum computing called the threshold theorem, which said something like this. If we can just bring our error rate per operation below some fixed threshold, it's on the order of 0.1% to 1%, then by scaling the number of qubits, we can exponentially reduce the errors. Let's say we can, even if we build a quantum computer that has a constant noise rate, we can actually perform a large-scale scalable quantum computer out of it. So what does this mean? This means that we can trade qubit quantity for qubit quality. In other words, if you have a very, very large number of qubits, you can make up for the fact that your qubits aren't that good individually and produce a quantum computation that still performs the correct thing collectively. But we need a certain qubit quality to begin with. There's an ante you need to meet. And until you meet this ante, scaling doesn't make any sense, basically, of the system. Okay. So where are we towards building a quantum computer? So in the 90s, when people were coming up with these theorems, quantum computers were really a pipe dream. So the forefront of research in the 90s was do a single 2-bit operation, and if this bit's 1, flip that other qubit, with error rate 10%. That was the forefront of quantum research. And what happened is over the first around 20 years of quantum computing's existence, there was slow and steady progress until at some point we got to the point around 2014 where we could do quantum operations with a 1% error rate instead of a 10% error rate. So that's a lot better. And people started getting really excited about this because 1% error rate is very close to that threshold or that ante you need to pay before scaling allows you to reduce your errors in your computation. So there's this one, for example, I remember this one paper by the Martinez group at Santa Barbara, which they made a 5-qubit system, and it's roughly at 1%, so they're near the threshold for this fault tolerance theorem. They're that's saying they're near the point at which scaling would actually improve their effective error rate. And this spurred a huge amount of investment in quantum computing. So if you plot like investing in quantum computing startups over time, like everything's zero before 2014, and then after 2014 it took off. This is kind of an out-of-date chart, but the graph definitely keeps going up to the right. This is on the order of billions of dollars of investment across industry in quantum computing. And these billions of dollars of investment have really paid off in improving the size and quality of quantum computers that we've been able to build. So now, after this 10 years of serious investment, we can now build quantum computers with hundreds of qubits and 2-qubit gates that are around 0.1% error rate. Like we've shaved another order of magnitude off of the error rate. And this is a real feat of engineering. Like some of these technologies involve things like manipulating the states of individual atoms on a lattice. Like these are really like pinnacles of modern technology. We've been able to do this. Okay. And there's a huge number of players who are trying to build quantum computers in this space. So they're both kind of the big players of industry like Google, Amazon, IBM, and Microsoft, who all have major quantum hardware efforts, and also a whole suite of startups. And even more. I don't have time or space to even list all of them, but here's a few startups that are kind of current leaders in the space. And what's interesting about these quantum hardware players is they're not all trying to build a quantum computer in the same way. So, a classical computer, you could build it out of a vacuum tube or transistors or even like, gears, like Babbage's analytical engine. Quantum computer is the same way. You can build a quantum computer a lot of different ways, basically out of any controllable quantum mechanical system. And these companies are actually pursuing totally different ways of building quantum computers from hardware. So for example, one of the leading architectures is something called superconducting qubits, where the qubits are little charges or flows of current around tiny loops of superconducting wire. Other players are pursuing something called ion traps or cold atoms, where they're actually manipulating quantum states of individual atoms on the lattice. There's a local company doing photonics, PsiQuantum, and Microsoft is pursuing another approach altogether called topological qubits. And where are we today? We've built these systems with hundreds to thousands of qubits, and the error rates are like in the 0.1% ballpark. Like we've made a huge amount of progress since the 90s. All right, and now for the bad news. Even though we've made this massive amount of progress, this is still not good enough. This is still not big enough to run these quantum algorithms that are going to change the world, right? So to give you like to bring things back to reality where we are today, like let's look at factoring. What's the largest number we factored with a quantum computer to date by running Shor's algorithm? The answer is 21. We learned that 21 is 7 times 3 with high probability after running the quantum device. Okay, so this is not anything very impressive, and you might ask, well, okay, there's a long way between that and breaking an RSA 2048-bit key. The estimate of like how big of a quantum computer you would need to break RSA 2048 is something enormous. Like one of the latest estimates I saw is estimating on the order of like 10, 20 million qubits would be needed in order to break an RSA key, and even that would take something like 8 hours. And the real challenge here is that Shor's algorithm is a polynomial time. It is an efficient algorithm, but it's very, very sensitive to noise. It's like a really, really high precision algorithm. So you need your effective error rate to be really, really small, like 10 to the minus 12. And even though there is a very good scaling of system size with error rate as you perform error correction, it gets exponentially better as you scale. 10 to the minus 12 is just a tiny number, so even the log of 10 to the minus 12 is like a very big number in terms of amount of overhead. Like the redundancies you're looking at building into your quantum computer to run Shor's algorithm are like 1,000 physical qubits per one logical qubit you want to perform the computation on. So if you want to run Shor's algorithm on a few thousand bit integer, it corresponds to a few million bits of that you would need in your actual physical device. So we're just very far away from doing this. Note, you should take these numbers with a grain of salt. Like these forecasts are based on projections of what will happen in the future with like how good future quantum hardware would be and what error rates will they achieve. They're very sensitive in particular to the future error rate. These assumptions are kind of assuming that we take a current error rates in the ballpark of 0.1% and we just make 10 million of them, of kind of the type of qubits we already have. If they improve it, then the overheads could go down. But the ballpark estimate that it's in the millions and not in the thousands is the right takeaway here. Okay, great. So, you're probably saying, okay, we factor 21, like what, that doesn't seem like a very impressive achievement to me. What is it that they've been doing with these quantum computers that has gotten them in the New York Times like every few months? Well, they actually have performed a good number of very important milestones on the way towards building a large-scale quantum computer. And the first one of these was an achievement called quantum supremacy, which was first claimed by Google in 2019. So in particular, in October 2019, Google performed an experiment that they claimed achieved quantum supremacy, which is the empirical demonstration of a quantum computation which exponentially outperforms classical computers. In particular, they performed an experiment on their chip called the Sycamore chip that took on the order of a few minutes that they claimed would take the Summit supercomputer 10,000 years to simulate on it. Right? And this is the first time that someone had done a large enough of a quantum computation to make this claim that they actually did something that was out of reach of any classical computer today. Now, how did they do this? Well, you might have hoped they did this with Shor's algorithm, but as I mentioned, we're kind of hopelessly far from doing this. Even though that would be a useful problem to solve, it's really hard to make a quantum computer do it. So it's been said that trying to demonstrate quantum advantage with Shor's algorithm is kind of like trying to demonstrate a chimpanzee is intelligent by trying to teach it to play chess. Like, yes, in principle, you could do that, but it's extremely difficult. It's kind of not naturally what occurs in the system. Well, what they've been doing instead is they've been solving something called sampling problems. And the philosophy is something like this. Well, quantum mechanics is naturally a theory where things produce random outcomes. So if you run a program on a quantum computer, it will naturally sample from some probability distributions over strings. And what the idea is to try to say, well, like, look at the probability distributions you can sample from with a quantum computer. Can you show a classical computer could not efficiently sample from those? In other words, can you just show a classical computer can't mimic what a quantum computer naturally does? That's more analogous to, say, demonstrating chimpanzee intelligence by just looking at what it does naturally in the wild and trying to see, well, are there any signs of something, very interesting here, like you're using tools or something like this. And this is exactly what they're doing. It means the problem that you're solving with your quantum computer is basically useless. There's a trade-off here. It's not something that we know to be useful for anything, but it does allow us to show that we've actually built a large enough quantum and high enough quality quantum computer to execute like a significant problem. So this is actually the type of tasks that they're doing in these articles that make it to the New York Times. So like one of the tasks they're doing is something called random circuit sampling. What's this? You just basically pick a random program to execute on your quantum computer, like the equivalent of typing like gibberish Python code. Okay, it doesn't do anything interesting. Run it on your quantum computer. That will generate some random samples. And just take some samples from this distribution and do that in order to demonstrate quantum supremacy. This task is kind of designed to be experimentally feasible. Like the task is like just mimic what a quantum computer does if you program it randomly. But actually my collaborators and I in 2018 showed some very strong evidence that this is actually something that's exponentially hard for a classical computer to do. So in other words, there is actually an exponential scaling as you scale the number of qubits that executes a random program. This is something that's exponentially hard for a classical computer to mimic. And this is what they're actually doing in these experiments that claim to have achieved quantum supremacy. So this Google experiment in 2019 was the first time they did it with 53 qubits. And subsequently, it's been done many times. Actually, in this last December 2024 experiment, they hit something like 70 qubit. demonstration. So when you read a New York Times article and you see that they say, oh, Google did a machine capable of tasks that a supercomputer could not master in 10 septillion years, where is the 10 septillion coming from? It's actually just coming from something like 2 to the 70. It's just that as you scale number of qubits, that exponential numbers grow very fast. So that's where these claims of large number of years come from. It's also been done, a related experiment has been done in optical platforms, both by USTC China and by Xanadu in Canada. I want to give the caveat that don't take these claims that this would take X years to simulate too seriously. In fact, the original Google experiment that they claimed would take 10,000 years actually has now been simulated on a GPU a GPU cluster with 50 GPUs in a reasonable amount of time. So don't take those absolute numbers as being important. What's important is that there is actually exponential scaling even in those simulation algorithms. So if you just increase the number of qubits, you'll eventually hit a point that's really hard. All right. So what did they do in 2024 that people were very excited about? Well, the main thing that people were excited about in this December experiment wasn't this 10 septillion years claim. It was actually the fact that they performed quantum error correction for the first time at scale. So in particular, they did the first large-scale error correction experiment where they saw an actual improvement in the underlying error rate of the physical hardware. So what they did, this was Google group, is they built a 105 qubit quantum computer, and they implemented quantum error correction using a particular error correcting code called the Kitaev surface code. And what they saw is that the error rate of the encoded information actually was better than the physical error rate of the hardware. That's it. They actually reached the crossover point at which you get gains from error correction. So if you plot the size of the code versus the logical error on the log scale, in theory, this graph should be linear. As you scale the code, your error rate decreases exponentially. And they actually just saw this line cross for the first time in 2024. They had done a 2023 experiment that got these data points, but these were this was an error worsening experiment. The encoded information was worse than the raw physical information. But now they're actually error improving experiments. They're actually showing that it works exactly as we predicted. And the error rate they estimate is roughly half of the threshold rate, which means as you scale the code distance d, that your effective error rate should go 2 to the minus d. So that's really good exponential scaling. So that means you merely need to scale their architecture to 10 million qubits, from 105 to 10 million to have a large-scale quantum computer. The other thing that we've seen a lot the last few years is progress in new forms of hardware. So, for example, in 2023, there was a hardware platform called Cold Atoms that did a 280 qubit experiment, also implementing large-scale error correction. And they actually, in their experiment, they picked up individual atoms and moved them next to each other to interact them, to implement kind of more efficient error correcting codes than you can do with superconducting qubits. It's a really cool experiment, and it really got people very excited in Cold Atoms as an alternative platform for building a quantum computer. And then more recently, just this February, Microsoft claimed to have produced what's called a topological qubit, which if they've constructed it as they claim, then it could reduce quantum error correction overheads in the long run. So that's kind of what this recent result was about. Right. So what's left to do? Well, there are kind of two things we need to do to build a quantum computer. First is improve the hardware, and second is improve the software. So on the hardware front, the obvious thing is to improve the number of operations that we can perform on the quantum computer before it devolves into noise. So now we're in the killa instruction set quantum error. We can do a killa operation on the quantum computer. And if you label the quantum errors by how many operations, how big of a quantum computation you can perform before your computer falls apart, there's mega, giga, and petascale errors. Breaking crypto systems lives somewhere down here, breaking your RSA 2048-bit key, breaking your Bitcoin or Ethereum digital signature. These are things that require a huge number of operations. It's very, very far away to where we are now. And there's a great question of like, when are we going to get to these intermediate eras, and what are we going to do with our quantum computers during this interim time? So there's a lot of excitement about using these kind of mega to gigascale quantum computers of the next 5 to 10 years for applications in material science and quantum chemistry. And I think we're still looking for more applications of these devices to see what sorts of problems they might be able to solve more efficiently. And there are also a lot of remaining challenges in theory. Both to kind of find new quantum algorithms, find like application discovery, find more uses for this model of computing. Also reducing overheads of existing algorithms so that as more qubits become available, we also reduce the number of qubits required to execute the algorithms. And also discovering new quantum error correcting codes that can reduce some of these error correction overheads are mentioned that are currently one of the biggest bottlenecks in executing a large-scale computation. There's actually been a lot of progress on theory of error correcting codes in the last few years. People are discovering more efficient codes than people realized existed before. And we still have yet to see how this will shake out, if this will actually reduce overheads in the space. All right. So in summary, what have we seen now? We've seen the first demonstrations of quantum computations that are beyond classical, and we've seen the first implementations of error correction. But these quantum computers are not useful yet. They're just too noisy and small. They're nowhere near breaking your digital signature, so you don't need to like lose sleep at this immediately. But merely scaling this technology to the hundreds to millions of qubits will unlock a new type of quantum computer that will require us to fundamentally change how we perform cryptography, and might also unlock new computational capabilities in say, material science and quantum chemistry. So I like to think of it as more we're opening a new paradigm of quantum computing, kind of like how the Wright brothers' first flight wasn't really useful for anything. It did at the same time open up, in the long run, a new frontier of human technology. And so this is definitely a space to watch if you're interested in the blockchains. All right, thanks. That's a great, so the question was, what's the intersection between AI and quantum computing? So there are some quantum algorithms for speeding up AI tasks, but they are relatively moderate speedups in that they're polynomial speedups. So we don't know yet if they'll be useful on a large-scale quantum computer. So it's unclear if quantum computers will, in the long run, help with AI. Yeah. Great question.
Actually, a follow-up to that, on the flip side, to what degree will AI accelerate the performance of quantum computing and maybe accelerate supremacy?
That's a great question. Like maybe we can use AI to search for new error-correcting codes or algorithms. There are definitely people thinking about this. Maybe that will reduce some of our overheads and bring quantum computing here sooner. So,
awesome.
Yeah, great question. Yeah, cool. Yeah.
You said in the beginning that the clock speeds of these systems are a lot slower than CPUs and GPUs. Does that physically have to be true?
It doesn't physically have to be true. And so the question is, I mentioned the clock speeds are slower. Does that have to be true? No, that doesn't have to be true. And different of these architectures have different clock speeds. Like broadly speaking, the cold atom ion traps are slower clock speeds. Superconducting qubits are pretty fast, and photonics are pretty fast clock speeds, much closer to tens to hundreds of, let's say tens of nanoseconds. So not that much slower than our current clock speeds. So yeah, great question. Yeah. That's a great question. So the question was, am I aware of Gil-Kalai or objections by similar research community members that quantum computers will never be able to be built? So a lot of times the arguments here, debates over here are like, what will the noise in a large-scale quantum computer look like? So if the noise is very correlated or adversarial across qubits, you can cook up noise models that actually hurt error correction a lot. On the other hand, the error correction or fault tolerance theorems are proven in models where you assume the noise happening on different qubits is relatively independent of one another. And that's where these techniques work really well. So far, the experimental data, in my opinion, looks like it's more on the independent side. So I personally believe Gil-Kalai is wrong here. But that's something that there's kind of discussions about. Yeah, great question.
Yeah, we got a question in the back over there.
The ETA for, oh boy, okay, so I'm a theorist, not experimentalist, so you're asking the wrong person. But you what's your feeling? Yeah. Oh, it's not in the next few years. It's more like a decadal scale thing, is my personal opinion. But yeah, but again, I'm not an oracle for the future. If someone just takes one of these technologies and actually scales it super fast, it could come sooner. could come later. I've also had an experimentalist once told me the rule of 3, which was just kind of however long you think it's going to take you to do a particular experiment, it will take you 3 times longer. So just take some of the timelines with a grain of salt when you see them. So,
I like
great.
that.
Thank you.
Stephen, did you have a question? Okay. Actually, one last question.
Sure.
Did Microsoft actually prove the multiverse?
Did they prove the multiverse? No, is the short answer. So the multiverse is one interpretation of quantum mechanics. It's mathematically equivalent to any other interpretation of quantum mechanics. So I don't think any of these experiments can really pick the correct interpretation of quantum mechanics. Great question.
All right, Adam, thank you so much. This has been awesome.